Okay, we're gonna look at an example that is very similar to problem one on project one. So let's take a look. All right, here's the circuit we're given. We have two resistors and we have a switch that's going to close at t equal to 0. And the problem is very much the same as what's in problem one, except in problem one, what you have is an inductor instead of a capacitor. So here, what I'm asked to do is determine the amplitude of the capacitor voltage long after the switch closes. And I'm told that to approach this, I should do the following. Write the differential equation for the voltage, solve for the steady state solution, and then take the amplitude of the result. Nowhere in there am I ever asked to do anything with the transient response. Nowhere in this problem am I asked to solve the transient response. Just as in problem one, you were never asked to solve for the transient response. So I want you to pay attention closely to how I do this, because really this is meant to be the way we would approach a simulation, right? That we don't have to do as much work because we can just let the computer do most of the work. Now, I am asking you some questions here that you need to solve, but all those questions really deal with the just the steady state response. So we're going to break this down and we're going to go step by step. Okay. So part A, determine the amplitude of the capacitor voltage long after the switch closes. To approach this problem, you should do the following. First, write the differential equation for the voltage once the switch closes. So, okay, here we go. Here's our circuit. Let's take this part. So once the switch closes, that means basically that this switch here is shut, right? So when I have a short across a resistor like that, what I have is that 0 equals I times R2, right? What I just wrote was KVL around that loop that includes the switch and the resistor. That means that the current in that guy is 0, right? So that means that there's effectively no current flowing through there. And the only loop that I have in this case, let me change my color. The only loop that I have is this loop, okay? So I do a KVL around that loop. Now, when I do my KVL, I put plus minus on my resistor there, and there's a plus minus on my capacitor already. So I say by KVL, 0 equals negative V sub S, and let me state that V sub S is the source voltage, okay? Negative V sub S plus V sub C plus V sub R1. All right, now what I do there is I just follow I go minus to plus, plus to minus on the capacitor, plus to minus on the resistor. So that means that V sub S, or 4 cosine 2 pi 10t minus phi equals V sub C plus V sub R1. Now, what you should know is that I sub C equals C dVc dt. So that means that I turn this into V sub C plus R1 times C dVc dt, right? Where C dVc dt is the current in the circuit. Okay, so for that, I make one last modification because this is perfectly fine. I can deal with this, but usually what I do is I usually like to get my equations in the form of x of t equals tau dy by dt plus y. I don't quite have that here, right? Because I've got, well, actually I do have that here. I guess I was thinking about the problem that you have on the project, which doesn't necessarily get itself right in that form, but I do here. And my tau is equal to R1C, which if I plug in the values for R1 and C, I'll see that this guy is equal to 1 second. Okay, so I've got my differential equation, all right, and I walk through how I came up with that. So let's look at part A dot B. Solve for the steady state solution of the differential equation, assuming phi equals 0. So what we had was 4, right? We had 4 cosine 2 pi t minus 0 degrees equals v sub c plus dvc dt, where I just plugged in the fact that tau in this case is 1 second. Actually, I'm going to leave the tau in there for now. Okay. All right. So how do we get the steady state solution for this? Well, we know that if I have a cosine as my input, I have a cosine as my output. So that means v sub c of t in steady state. So our steady state solution, steady state is the particular solution, right? Is of the form magnitude b cosine 2 pi 10 t plus angle of b, which we know is the real part of b e to the j 2 pi 10 t, where b has some magnitude and some angle, okay? And we're going to solve for it like that, okay? So we talked about this approach in dealing with differential equations. We talked about kind of a 5-step process for doing this, right? I make this guess, and then what I do is I convert this whole differential equation into the Phasor domain. So the Phasor domain equation we'll write that out, is going to be 4, and so I said 4 cosine 2 pi, sorry, that should be 10t minus 0 degrees. That turns into 4 e to the j 2 pi 10t, right? Because if I took the real part of that, it would turn into 4 cosine 2 pi 10t. And that's equal to v sub c plus, and maybe I should be really careful because we're talking about the steady state solution, and I've always labeled that with a p. So we'll say this is our steady state solution or particular. All right, so I'm not doing anything with the transient. Okay, so I have v sub c p plus tau times dvc p dt. So what I do is I put my guess into there, and I say that 4 e to the j 2 pi 10t is equal to b to the j 2 pi 10t plus tau times the derivative with respect to time of b e to the j 2 pi 10t. Now you should know by now, if I take the derivative of that thing, that just brings the j 2 pi 10 down, and this whole thing becomes b e to the j 2 pi 10t plus tau times b times j 2 pi 10 t, well, not t doesn't come down, right? Just the multiplier on the t, and that's multiplied by e to the j 2 pi 10 t. Now all of this was equal to 4 e to the j 2 pi 10 t, right? Just carried that down, right? One thing I see right off the bat is every term in there has an e to the j 2 pi 10 t, so we get rid of those. So I go to my next slide here, and it looks like what I have left is 4 equals b times what? B times 1 plus tau. I'm going to group my terms a little differently. 1 plus j 2 pi 10 times tau. Right? That is basically just grouping the terms, if you want to watch that carefully, just grouping the terms that I have here and recognizing that there's a b in both of those terms. All right, now the thing I'm trying to do is I'm trying to solve for b, and we remember that b is equal to a complex number, so it has both an angle and a magnitude that I need to solve for, okay? So to do that, I basically say, okay, well, magnitude of b, so if I take the magnitude of both sides of this, I guess, I say 4 equals the magnitude of b times the magnitude of 1 plus j 2 pi 10 tau, like that, right? Because the magnitude of two numbers multiplied by each other is just you multiply their magnitudes. And then I have an equation for the angle where I say the angle of 4 equals the angle of B plus the angle of 1 plus J 2 pi 10 tau, like that. Okay, all right. So now I just got to solve for those angles. So in this case, I say the magnitude of B equals 4 divided by the magnitude of 1 plus J 2 pi 10 tau, which would be the square root of the real part squared, that's 1, plus the imaginary part squared, which would be 2 pi 10 tau squared, okay? And then on the angle side, I have the angle of B is equal to the angle of 4, which is 0 degrees, minus the angle of 1 plus J times 2 pi 10 tau. I turn that whole thing into negative arctan of imaginary part over real part, so just 2 pi 10 tau. And again, I don't have to do anything funny with that angle because I know that complex number 1 plus J 2 pi 10 tau, that complex number would be in the first quadrant, right? I know that both the real part and the imaginary part are positive. Okay, so with this I can solve. Now what I do to solve for this specifically, right, is in my case, what I did, I wrote a MATLAB script that just said the complex number B is equal to 4 divided by 1 plus J 2 pi 10 tau, which if you look, the magnitude gives me that relationship, the angle gives me that relationship. And so the way I do this is I have my code here where I put in all of my numbers, right? So I put in C, R1, my R2 value, which I don't need right now. I want my phi to be 0 degrees, so I'll make sure to do that, right? And then what I have here is my B value, okay, that I use in this equation. And I assumed that my source could potentially have an angle, right? But for now, what I have is I'm keeping that angle at 0 degrees, okay? And so what this is that equation for B right here, right? So I have 1 plus J omega times R1 times C. And notice I've defined omega to be 2 pi 10, which is what we have in the problem. So if I run this and I take the magnitude of B and the angle of B times 180 over pi, I'll get the magnitude and the angle in degrees. So I evaluate that and I look at what I get in my result. It tells me the magnitude of B is 0.0637 and the angle is about negative 89 degrees. So I will say that the angle is negative 89 degrees. And the magnitude is, what did we say it was? 0.0637, I think was what we said. 0.0637, 0.0637. So that tells me at the end of the day that my V sub C steady state is the real part of the magnitude of B times e to the j angle of B times e to the j 2 pi 10t, or simply 0.0637, which is the magnitude, times cosine of 2 pi 10t minus 89 degrees, right? That's our steady state solution. We don't need to find the transient. That's our steady state. Part C asks me to take the amplitude of the result. The amplitude of the result, I guess I'll call it V sub Cp amplitude is equal to 0.0637 volts. Okay, that should be fairly straightforward. Notice I did nothing in there with the transient. I wasn't told to. All right, part B. Now I'm going to write code to solve for the voltage numerically. All right, this is what we learned how to do on September 23rd. All right, so you should go back and look at how to do that. I'm gonna try to go through that process with you. All right, but it basically tells me that I needed to go through a couple of steps. So let's watch those steps. So first is determine appropriate time step delta t. Do this by considering the form of the transient solution and the form of the steady state solution. So what we have here is what? We have v sub c. Let's write the differential equation again. We have 4 cosine 2 pi t minus phi equals v sub c plus tau times dv c dt. Now, for this, we don't have to solve for the transient, but we have to know what the form of the transient solution is. And we know that for a first order differential equation like this, we're always going to get that the solution to this guy has the form v sub c of t, v sub c of t is equal to some constant times e to the st plus magnitude of b cosine omega t, and that omega, I guess I can be explicit, in this case is 2 pi 10 t, all right, plus the angle of b. And I note that I left out the 10 when I wrote this up here, right? 2 pi 10 t minus phi, like that. All right, that's the form of my solution. I know what the magnitude of b is. I know what the angle of b is. I don't really care. If I were to try to solve for the steady state to figure out what s is, you should know. If I had to do that, I would say, well, it equals, 0 equals 1 plus s tau is the characteristic equation I'd get for this guy. So s equals -1 over tau. You should know how to do that, right? So I basically have c e to the negative t over tau plus magnitude of b cosine 2 pi 10 t plus the angle of b. Now what we said is we have two kind of time features here that we consider, right? One is the exponential and the other is the sine wave. We want to be able to see both of those. So we need to choose a delta t that is small enough to capture both of those time features. So to do that, I say, well, to capture an exponential is over in about 5 tau. So if I want to see that, I need to make sure that my delta t is much, much smaller than 5 tau. Okay. If I want to see the cosine, I need to make sure that my delta t is much, much smaller than the key time feature of my cosine, which is the period, which in this case is 2 pi over 2 pi 10, or just 0.1 seconds. Right? And my tau, I solved for it with the R1, so my tau, you can go back, you don't remember it, tau is R1 times C. That is, in this case, simply 1 second. So this is 5 tau would be 5 seconds. Okay? So if we want to capture the time feature, what I see is that my delta t should be much, much less than 5 seconds, all right? Or much, much less than 0.1 seconds. So what we said then is much, much less than is, let's say something like 1% of that value. So 5 divided by 100, right? So 5 divided by 100 would be 0.05 seconds. Or my delta t could be chosen by saying delta t is 1% of the period. So 0.1 divided by 100 becomes 0.001 seconds. So what this says is I needed to choose the time step that was small enough to capture both features. So in this case, it looks like it's going to be this one, right? It's the period of that cosine that sets my choice. And if I choose that value, anything less than about 1% like that, it's going to be small enough to capture both of these. So in this particular case, I can write my code however I want. I actually chose in my code that my delta t was equal to the period divided by 1,000. Okay, is what I did. All right, so part B, determine an appropriate end time for your simulation. Your graph must show at least 2 complete periods of the steady state voltage and at least 7 tau. So one thing I can see here, so T end, I'll call it, so the end time, could be, one choice would be 7 tau. So this would be, I guess I'll call it choice 1. Would be 7 tau, which we said tau was 1 second. So this is 7 seconds. Or we have choice number 2, which is that T end could be, as an alternative, 2 periods. So I want to be able to show at least 2 complete periods of the steady state voltage, and this is the key thing, and at least 7 tau on the transient response. So 2t, that was 2 times 0.1 seconds. So that comes 0.2 seconds. So if I want to be able to see both at least 2 periods and 7 tau, that tells me that this choice is the one that will ensure that I see both. Okay. Sometimes it's going to be different depending on the problem. All right, so when I define my t vector, I'm going to say it starts at 0, goes in steps of delta t, and I would write my MATLAB, I would, the way I would write this is I would say delta underscore t up to t end, which in this case would be 7 times tau. That's the way I'll define my time vector. Okay. Now, part B dot C, I think, is where we actually write the equation. So write a MATLAB script that solves for the voltage V sub C of t after t equal to 0. Solves for this numerically, right? Back to my original problem statement. I want to solve for it numerically. That means I got to convert this into discrete time equations. So I want to give myself plenty of space to be able to do that work. Put another slide in here. Okay. So my equation, I'm going to say, is this. It's V sub S of t equal to V sub C of t plus tau times dVc dt. And I have to discretize that, which means that I go back to the notes that we had on the 23rd of September. And I see that I would convert that into a, using this approximation, I say, go back to the definition of the derivative and say this guy would be approximately V sub C of t plus delta t minus V sub C of t all over delta t. Right, so what that does is if I use that approximation in my original differential equation, I get V sub S of t equals V sub C of t plus tau times, and now what I do is I insert my approximation of the derivative. So I put in here V sub C of t plus delta t minus V sub C of t all over delta t. Now I have some algebra to do. What I do is I solve for V sub C of t plus delta t using, so I solve for this in terms of, I'll say as a function of V sub C of t, V sub S of t. In other words, I'm solving for a future value of the capacitor voltage based on what the capacitor voltage and the source voltage are right now. Okay, so I have a little bit of algebra to do to make that work, right? So to do that, what do? What I do is I multiply both sides by delta t over tau, and I get V sub S of t times delta t over tau equals V sub C of t times delta t over tau plus V sub C of t plus delta t minus V sub C of t. And again, I am solving for this guy, just doing algebra now. So if I rearrange that whole thing, let me see, I want to copy that. If I can. Not gonna let me copy that. All right. I'm going to write that again, I guess. Vs of t times delta t over tau equals V sub c of t times delta t over tau plus tau plus V sub c of t plus delta t minus V sub c of t. So I go through and I solve for this guy, and I end up with V sub c of t plus delta t equals what? It's going to equal V sub s of t times delta t over tau plus V sub c of t times 1 minus delta t over tau. And what I did here was to move these two terms to the other side to be able to solve for that. Okay. So, the way that I then put that into code is like this. All right. Here's how I put that into code. Oops. All right. So I defined V sub s here. All right. So V sub s for cosine omega t, omega is defined up top as 2 pi 10. Right now I have minus phi. So I wrote this the same way I have in the problem statement, except right now I've been told that phi equals 0. And I was also told that the initial condition is V sub c underscore 0. My initial condition is 0 volts on the capacitor. I create an empty vector for the voltage on the capacitor, and I create the V sub s vector. And I did that defining the time vector that I had up here. Remember, this is what I talked about before. I had a delta t was 0.1 divided by 1,000. And I set up my t vector to be from 0 in steps of delta t up to 7 tau. We walked through those steps above. What I did was I defined basically two things. I had this term here. I called this A, and I called this term B. And bring that script back up so we can see that. Right? So A is delta t over tau. B is 1 minus delta t over tau. And then what I did was I wrote a simple little script that solved for the next value of V sub c in terms of V sub s and V sub c. Now what I did here, the thing that's different is what I said is I don't need to keep the time representation in here. I say that V sub c of, so we remember, right, that our time vector is n delta t. That means that, so if I generalize this, I say that V sub c equals n delta t plus delta t, or V sub c of n plus 1 times delta t. And I plug in t equal to nt in the other side of this whole thing, and I end up with V sub c of n plus 1 equals V sub s of n times a plus V sub c of n times b. Right? I make that substitution and say that the next value in the capacitor voltage is dependent on the current value of the source voltage and the current value of the capacitor voltage. And I have my script do that for me here, right? That's what my script is doing. Let's put that on top, right? V sub c of n plus 1, a times Vs plus b times Vc. I run that, and I'm going to make a graph. All right, so let's highlight that, evaluate selection, wait for figure 1 to update, and there it is. And notice I don't see much of a transient response to this here. There is one. I can see it a little bit. When I solve the differential equation numerically, it's just solving the differential equation. So it's giving me the transient and the steady state. I am not asking you to solve for the transient. This is a very common thing people do when they look to find the whole complete solution, is they just solve it numerically. Now, once I get to steady state, which should be somewhere out here, I should be able to see that the peak value matches what I calculated. So let me use my data tip here. So I click on this tool here, right? And I see that the peak value there looks like it's 0.0636. And what did we say it was? We said the peak value in steady state, 0.0637. If I rounded differently, I would have gotten the exact same thing. Okay, so I did everything right up until now. Now, part B.D says, once my code works, try several different values of phi between 0 and 180 degrees. For what approximate value of phi does the value of v sub c become the largest after t equal to 0? All right, so what I'm going to do is I'm going to try these different values. And I remember that the way I'm told here is that I have 4 cosine 2 pi 10 t minus phi. So what I did in my script, is I defined phi to be 0, okay? And then I plugged it in to my v sub s like this. Now, you could write like a for loop or something, probably, to try a couple of different values, and to plot them all and do some fancy stuff. I'm just going to try these values and see what happens. So what I'm going to do is I'm going to say omega equals to 45 degrees. And I'm going to run this again. And evaluate selection. And it takes it a second to run. There it is. Now, what I see is the transient response has totally changed. So let's see, what's my maximum value now? My maximum value that I obtain here, so I'm using the data tip again. Looks like it's somewhere around 0.106. All right, so let's say it's, I'll round up. Okay, so 0.106. Now let's see what it is at 90 degrees, shall we? 90 degrees. At 90 degrees, again, this is why you could use a for loop to do this sort of thing, but I'm just going to do it by hand. Oops, went too far in my script. Evaluate selection. And I see what my maximum value is. All right, so it takes it a second to run. I see it's a little bit higher. It looks like it's, if I try to really get it to the peak, it looks like it's about 0.124. Now, without me spending all the time going through this, right? Because you guys can go through this yourself. What you're going to see is as I go past 90 degrees to 135, 180, I'm going to see that the values come back down again. So this one here is the approximate value of phi that gives me the maximum. Explaining that and going through that kind of a process is what you need to do in your project. Okay. All right. So part C. All right, part C. You're now going to determine the impact of phi. All right, write the differential equation for the voltage before the switch closes. Okay. So what we're going to do, in fact, the thing I'm trying to do is trying to impact of phi. What I want to do is I want to, write the differential equation, solve for the steady state solution of it, rerun my simulation with phi and my true initial condition, and figure out what the peak voltage is in this condition. Okay. All right. So let's do that. So let's do part A. Write the differential equation before the switch closes. So this switch is still open. Now, I look at that and I say, okay, well, before the switch closes, I look at this. This is actually almost the exact same circuit in a way, right? Because what I have now is 2 resistors in series. So really, I could think of it as being the exact same differential equation, right? Vs sub t equal to V sub c of t plus tau, where my tau in this case would be R1 plus R2 times C dV c dt. You should be able to see right? It's just, I could combine those two series resistors and effectively it's the same circuit. All right, so I get that as my result. So that's a fairly straightforward thing for me to do. Now in part B, solve for the steady state solution using the value of phi that you found in part B dot D. So we found in B dot D, if we look back there, right, I found that my phi was about 90 degrees. So, all right, so I know what I need, all right. I'm going to say that to solve this, I have 4 cosine 2 pi 10 t minus 90 degrees equals v sub cp of t plus tau dvcp dt, like that, right? Where v sub p, or vc sub p, okay, this is our particular or steady state. Because we have a cosine as my source, I know that I have a cosine in steady state. So it's going to be the magnitude of b cosine 2 pi 10 t plus angle of b, or the real part of b e to the j 2 pi 10 t, where b is equal to a complex number with a magnitude and an angle, like so. Okay, so we take the whole equation again into that complex form, that Phasor form, and I say I have 4e to the negative j 90 degrees equals b e to the j 2 pi 10 t plus tau times d by dt of b e to the j 2 pi 10 t. Now I go through that same process as I did before. Isn't any different, right? I take the derivative and all that sort of stuff. What I end up with is that 4e to the negative j 90 degrees equals b e to the j 2 pi 10 t times 1 plus j 2 pi 10 tau times b, right? So I know that I'm going to get a common factor of b e to the j 2 pi 10 t when I solve this thing, right? And if I was careful, I guess I left out the fact that if I'm truly in the Phasor domain, I just say 4e to the negative j 90 degrees times e to the j 2 pi 10 t. So I need to put an e to the j 2 pi 10 t in front of that whole thing. And the e to the j 2 pi 10 t's are going to cancel, right? So if I look at this, what I have is 4e to the minus j 90 degrees equals b times 1 plus j 2 pi 10 tau. So b is equal to 4e to the minus j 90 degrees divided by 1 plus j 2 pi 10 tau. Now, if I want to find the magnitude and the angle, pretty simple. Magnitude of b is the magnitude of the top divided by the magnitude of the bottom. Magnitude of the top is 4. Magnitude of the bottom is 1 plus 2 pi 10 tau squared. And for the angle, I have the angle of b equals the angle of the top minus the angle of the bottom. So negative 90 degrees minus the angle of 1 plus j 2 pi 10 tau, which if I solve for that, right, that's going to be an arctan. Again, the way that I do that here is I go to my MATLAB script. Okay, go to my MATLAB script. Now what I've done is I've said R1 is 1,000, R2 is 100,000. That's the value that I'm given in the circuit, right? 1,000 ohms, 100 kilo ohms. Okay. And in part C, okay, I knew my phi was 90 degrees because I was told to use that. Now, what I have here, here's my B equation. Now notice I have tau defined a little bit differently, but that's actually for something later in this problem. The way I look at this, the tau that I'm using in this particular case is R1 plus R2 times C, right? Before the switch opens, sorry, before the switch closes, right? Before the switch closes, my tau would be set by the sum of those two resistors, right? So I have, all right, this equation here, 4 times exponential j times degrees to radians, negative phi here. So my phi was 90 degrees, all right? So this is taking negative 90 and converting it to radians. And on the bottom, I have 1 plus j omega times tau. My tau was R1 plus R2. And then I take its magnitude and its angle. So let's run that and see what we get. All right, so I look to see what I get in the command window. Looks like I get 6.3 times 10 to the negative 4. So angle of B is 6.3 times 10 to the negative 4. And the angle there looked like it was about negative 179, right? Was it? Negative 179.99, which is really 180. But I'll just call it that. All right. That tells me my steady state solution, B sub C, P, right, is going to be very small, apparently. It's going to be 6.3 times 10 to the minus 4 times cosine 2 pi 10 t minus 179.99 degrees. Okay, that's our steady state solution. Part C dot C, using a result from part C dot B, so the one we just got, determine the true initial condition for B sub C of 0. So the true initial condition, meaning that what we care about is when this switch closes. So if that switch had been open for a long time, we would be looking at the steady state solution to this guy to really tell us what the initial value of the voltage was, right? So in this case, what I got to do is I got to say, well, the value I had was that V sub P. I plug in 0. I don't need to worry about the transient response because this guy's been running for a long time. The transient's long since dead. So I just plug that value in here, which apparently is going to be 6.3 times 10 to the negative 4 times cosine of 2 pi 10 times 0 minus 179.99. That value, whatever that is going to be my initial condition now that I'm going to plug in. Now, the way that I did that in my MATLAB code, okay, the way that I did that in my MATLAB code here is I said, all right, now my new initial condition is the magnitude of B cosine omega times 0 plus the angle of B. Notice I said angle of B because I know that's going to be a number in radians. Okay, so then what it says to do, rerun your simulation from part B with phi and your new V sub C of 0. So we found that phi was equal to 90 degrees. And we found this guy was whatever it was we just solved for, right? And we rerun this thing, okay? And in particular, the key thing is you're asked to run your simulation from part B. This means that you're rerunning it after the switch closes, okay? That's the important thing. You're running it for after the switch closes. So basically, you know, I don't need to change anything about the equations that I converted to discrete time. Everything's the same, my A value, my B value, all that sort of good stuff. B sub S, you know, the thing here is I set my phi value to 90 degrees, and I'm using this true initial condition, okay? So now I'm going to rerun this whole thing, and let's see what I get. Give it a second to run. All right. I see what my peak value is here. Now, nothing, because I'm rerunning it from part B, I'm doing it after the switch closes. My steady state value, if I do a check in steady state to get the true value, nothing should have really changed here. Let's get the true peak value. Yeah, 0.0637. That's exactly what we said it was. Or so the peak value in steady state. If I look at the true peak value that I get during the transient, the highest value you ever get, right? Looks like this guy is 0.123, right? So in the last part, C dot E, it asks me what's the peak voltage now. It looks like it's 0.123, okay? So that's all we got to do here. I'm not asking you to numerically solve for something like this. I'm not asking you to solve that by hand by any stretch. I'm asking you to solve the differential equation numerically and then just use your results in MATLAB to be able to answer those questions. All right, so hopefully this video will help you to kind of process through how to approach this. Now, what I'll also do is give you guys a sort of how would I have written up something like this, so you can use that as an example.